Hi guys, in this short video we're going to look at the limitations of the wave function, and of course this is going to be a contribution or a complementary video on the concept of the significance of the wave function. Now in our last discussion we had said that we can represent the wave function in various forms by considering a volume element in space, and we had said that if we're going to consider volume element in space over dx, dy and dz, we had said that this can be given in terms of the integral between 0 and infinity for this summation of three elements over space, whereby we're going to have this one represented as the square of this function dx, dy, dz, and this is equivalent to 1 if we're going to find that particular in space. And then we said that if we have the dx, dy, and this is going to be the xy plane, and of course we're going to consider this one therefore that if our particle is confined with this xy plane, then we can represent this specific probability by having it or using this normalized equation using this specific representation for dx dy. And then lastly we said that if we have this particle confined within the x-axis, then we can have this normalized equation given in terms of so this is going to be given as dx. Therefore we're going to have the integral between 0 to infinity of this wave function given in terms of dx equivalent to 1. And I've given the last example for this representation and said that this basically can be given an example of a particle in a box, which is going to open for us a way of finding the probability of finding a particle in a given volume in space. So today we're going to look at the significance or the limitations of this particular wave function. And of course, first we're going to mention a number which are going to be applicable in this particular case. Now for this particular aspect of the wave function, we're going to see that for us to use it in solutions for Schrodinger's wave equation, the aspect of this wave function is that it must be finite for all values over x, y, and z. So therefore it must be finite. So this is finite for values over x, y, and z. So that's one of the limitations that we're going to see. And then limitation number 2 is that it must be single valued. Now this implies that for the values over each of the values over x, y, and z that we have mentioned, there's going to be only a single value representing this specific values for x, y, and z for this particular wave function, and that's going to be one of the limitations in its application for finding solutions for the Schrodinger's equation. And then we're going to have this limitation number 3, whereby we're going to see that it must be continuous for all the regions except where the region where the potential is infinite. So it must be continuous for all of the regions, as we have said, except where the potential is infinite. And this region where the potential is infinite is a region whereby we had said this specific value for a is greater than a. For a single, of course, an infinite well, we had said that this region is between 0 and a for the values of x. Now for the region whereby x is smaller than 0, this is going to of course encompass this limited or restricted region at this point and this point, which is outside the box. So at this specific point that we're going to have infinite potential, and in this specific space, then therefore we have said that the limitation number 3 says that it must be this particular function must be continuous in all region except where the potential is infinite, which are outside those specific region we said is a restricted area. And then we're going to have the limitation number 4. For this wave function, for the limitation number 4, we're going to see that it's analytical in a sense that the first order derivative is going to be continuous. So in a sense it must be, so this one is analytical. The wave function is analytical in a sense that the first order derivatives, or it possesses a first order derivative that is continuous. And then lastly, we're going to see that this specific wave function, it's going to vanish at the boundaries. Now we are given one of the conditions for these two specific functions for the wave function and the square of the wave function, whereby we say that at the boundaries, the value of this specific wave function must be 0 in order to avoid this aspect of discontinuity. So therefore, we're going to see that it is one of the limitations whereby we're going to see that the boundaries, this one has to, or it furnishes the boundaries, and that's one of the limitations that we're going to see. So this, among others, are going to assist us have a clear picture of this specific aspect of the wave function that we're going to use in a Schrodinger's equation. And of course, I'm going to put a link of other videos which we have discussed on various principles of quantum mechanics in our description box of this specific video. So check them and kindly open the links to learn more about this specific aspect of the wave function. So that is it for now, guys. Bye, God bless you. Catch us in our next video.